before that fluid had to support the weight of the water that was in there. So now it still exerts the same force because the fluid is exactly the same. And therefore the force it exerts upward is the weight of the fluid that was displaced. Okay, so a typical situation is, let's take a vat of liquid, and in it, let's place a cylindrical disc. And let's let the disc have a radius r, and have a height capital H. Let the density of the disc be equal rho m, and the density of this be equal to rho fluid for the fluid. Now what I want to know is to what depth h will this thing sink? Okay? Now, what's the criteria? It will sink until there's no net force on it. There'll be no net force on it when isolate this critter, write down the sum of the forces. It will be mg directed down, which is the density of the thing, rho m, times its volume, which is pi r squared times its height, which is h, times g. And then there will be the buoyant force up. Now, the buoyant force up will be the weight of the fluid displaced. And therefore, it will be the mass of this chunk of fluid, which is the density of the fluid times the volume that's displaced, which is pi r squared times little h. And therefore, the equilibrium condition is that when F buoyant equals mg, and therefore rho f pi r squared h must equal rho m pi r squared h, and there's g here, of course. G. And most of this stuff cancels out, pi r squared g. And so you get h is equal big H times rho m over rho m. Or actually upside down, of course. No, that's right. Okay, so if the density of the block is less than the density of the fluid, then little h is less than big H, and the thing floats. When they become exactly equal, it'll just submerge. Any more than that, and it sinks to the bottom. All right, so how come steel boats float? Because they're hollow.
So its density
So
overall is less.
what you have in the case of the steel boat is a shell on the interior. The fluid displaced is still what it was before, but the mass is not this volume, it's just the volume of the steel shell.
Cool.
Okay? That's pretty trivial stuff. That makes sense to everybody?
Yeah.
Only key thing is the buoyant force is the weight of the fluid displaced. As long as you got that, everything else is simple. Now there's one other very common application of this stuff, and that is to hydraulic lifts. So let's suppose that we have a system like this, where we have two pistons, this one and this one. And I'm going to push down on this piston and raise that. And the question at issue is, I exert a force F1 over here. What force do I get over here? Nothing is going to be useful. We need to get F2 bigger than F1, so that I can exert a small force and lift a car. All right? Now, we know that the pressure is the same at the same depth everywhere in the fluid, which means the pressure is the same here as it is over here. But if this area is little a and this area is big A, then the force F1 is the pressure times little a, and the force F2 is the pressure times big A, and the pressures are the same, and therefore F2 is equal to F1 times big A over little a. And by simply making the area of the piston where I want the big force to be larger than the area of the piston where I'm applying it, I will get my force multiplier. Now, did I get something for nothing? In other words, how about the work done in raising the object? Well, the work done is the force times the distance moved. And so the work done by force 1 is F1 times the distance moved. Let's call this L1. Okay? Now the work done over here that I got out was F2 times L2. But what I know is that the area of the volume of the fluid is fixed because the fluid is basically incompressible. And so I know that A1 and AL1, that's the volume of the fluid that was moved from the left side to the right side, must be equal to AL2. And therefore, L2 is equal to L1A over A. And so over here, we have F1 times A over A times L2, which is L1 little a over A, F1 L1, exactly the same as I put in on the other side. The only difference is I now exert a small force over a large distance to get a large force over a small distance. Okay, well that's fluid, static fluids, and they're pretty simple. But of course, they're also not very interesting. The interesting stuff is when we talk about fluid dynamics. What happens when we have the fluids moving instead of static? Now, this is a very complicated problem. We're going to look at a simple limit. Now, to get an idea of how complicated it is, go look at any stream. You look at a stream, do you have a nice smooth flow of water down the stream? No, you got eddies and swirls and backwaters, and I mean, it's a terribly complicated mess. Now, that which we refer to as turbulent flow, is, as I say, extremely complicated problem, and we're going to say very little about that. I'll give you some general principles about it, but it's just very complicated. However, there is one situation in which fluid dynamics is pretty straightforward, and fortunately, it very often applies. And that is the situation where we have what's called laminar or streamline flow. And what we mean by that is that if you have at one point in the stream, particles in the stream moving like that, then whatever happens, they may spread out or whatever, but particles that were close to one another in the beginning will stay close to one another. They will not do this. They will stay basically close together. Now, when that happens, we call it streamline or laminar flow. And that situation is easy to describe. It's easy to figure out what's going to happen. It's particularly easy to figure out what's going to happen if the viscosity is low and the fluid is incompressible. Now, most liquids are pretty incompressible. The viscosity in liquids is reasonably low. And so it isn't a bad approximation for fluids to claim that the density is fixed and there's no viscosity. Now, it would appear that there'd be no viscosity for air, for gases, but the density would not be fixed. Turns out, numerically, if you put in the appropriate pressures and volume and change in volume that you get, change in density you get, that even for gases, it's a pretty good approximation. It's not obvious. We can put in some numbers that demonstrate that. But it turns out that even for gases, it's pretty good under most conditions. So let's suppose we're dealing with a situation where we got laminar flow with no viscosity and with incompressibility. Then we can analyze how fluids will work simply by applying conservation of energy. So let's create a generic situation like this, where you got fluids coming in to a pipe which changes its elevation and changes its area. So let's choose to measure things from this level and call this H in and this H, well, let's just say H1 and this H2. And let the area of this be A1 and the area of this be A2. And let the velocity here be V1 and the velocity here be V2. And the pressure here be P1 and the pressure here be P2. Now, since the flow is laminar, once I get into the region where nothing is changing, then the flow is just going to be parallel to one another and parallel to the base. All right? So now, let's imagine we carry a little bit of fluid from here over here. Now, we need to write down conservation of energy. Now, if the density of the fluid is rho, which is going to be the same both places because we're assuming it's incompressible, then the kinetic energy plus the potential energy at 1 plus the work that was the energy that was added to it by doing work on it on the left side must equal the kinetic energy plus the potential energy N2 plus the energy that you took out over here. Now the kinetic energy is 1/2 mv squared. And so it is 1/2 rho times the volume. Well, let's look at it for a little chunk of time dt. Then the volume is A1 times V1 times dt. Because the length will be the distance that this little chunk moved, which will be V1 dt times the area, and then V1 squared. Now the kinetic energy will be the mass, which will be rho A1 E1 dt times g times the height, h1. Now, the work that is done on this from the outside, pushing it in, will be the pressure, P1, times the area, that gives the force, times the distance moved. So, P1, A1, that's the force, times the distance moved, which is V1. So that will be the left-hand side. That's the energy we got to account for. Now, on the right-hand side, this will be exactly the same as this when I change the 1's to 2's. So I will have 1/2 rho A2 V2 dt V2 squared plus rho A2 V2 dt g H2. Well now, as this fluid leaves, it will do work on the stuff over here, which is the force times the distance that it moves. And the force is V2 A2, and the distance moved is V2 dt. So that is the statement of conservation of energy for a little chunk of fluid that enters on one side and then ultimately leaves on the other. Now, because the density is a constant, it must be true that the volume A2 V2 dt is the same on both sides. Otherwise, the density would be increasing or decreasing. So that must be the same as A1 V1 dt. So I can cancel all those out. And then the bottom line is that you get P1 plus rho g H1 plus 1/2 rho V squared equals V2 plus rho g H2 plus 1/2 rho V2 squared. In other words, in such a fluid, the pressure plus the potential energy plus the kinetic energy is a constant. And that is known as Bernoulli's principle.